All right, AB Calculus BC, Unit 6, Day 4. This is going to be exponential growth as well as logistic growth. All right. So exponential growth was part of Calc BC's material, and logistic growth is also on BC. So let's see, we could do a quick review of exponential growth. I'm going to do two different sides here. So we'll start with exponential growth. Exponential growth. So I'm going to use like this much of the page, and then the other side I'm going to do logistic on. So just a quick look at the graph. A lot of times it involves t, and the graph looks like this. It blows up. It goes towards a horizontal asymptote. Y equals 0. Generally goes through 0, 1, and whatever the initial condition is. Say 0, why not? And the description of exponential growth, even going back to maybe when you've were introduced to it many, many years ago, maybe even Algebra 1, says something like the rate of change or the growth rate is directly proportional to the current population, current amount. A lot of times we do apply this to, population. So, but it could be, whatever, a lot of different things can be exponential. This phrase right here is actually describing a differential equation. So very, very appropriate for this unit. Down with a lot of differential equations. So if we were to translate this in a sort of calculus notation, rate of growth, rate of change, growth rate, that's a derivative. That's a dy dt. And then directly proportional means there's some constant, which often we use k, to the current population. So that whole phrase translates into this. This is called the constant of proportionality. For us, it's going to actually be, it's going to end up being a growth rate. So we could solve this differential equation, separate the variables, integrate both sides. Natural log the absolute value of y equals kt plus c. Okay, I guess we're just going to leave the c there. We're going to exponentiate both sides. I mean, you guys shouldn't even have to wait for me to write the next line. We've been already practicing this chapter. I'm going to get absolute value of y equals, and I'm going to use properties of exponents to split this up. And then that's just a new constant. To get rid of the absolute value, we're going to do plus or minus. So I'm going to just call it e to the cc and just put it in front. And the c is going to probably take care of the plus or minus. But we often write it like this for exponential growth. Y equals y naught e to the kt. But that's the exponential growth equation that you've been using for many, many years. And that's where it comes from. That's the derivation of it. And we did that last year. So now the thing about it is that's cool, but a lot of things don't really grow purely exponential because you can't just have like unbounded growth that just grows forever. Things blow up, especially natural things. So we need maybe something a little more realistic. I mean, in the long run, this isn't very reasonable. So that's where logistic growth comes in. And so logistic growth, let's take a look at the graph first. So it's a little more realistic growth model. Sort of limited resources, limited growth. Growth just doesn't continue to blow up. So the graph looks like this. So this limiting, this ceiling of how much the population can really grow, and we like to use capital N. It's called the carrying capacity, and this is something that you may have studied in other courses like bio, logistic growth. They call it carrying capacity there. There's this interesting thing that happens exactly half of the carrying capacity. And there is a horizontal asymptote here. And in fact, the carrying capacity is going to be the other horizontal asymptote. And the graph looks like this. At first, it looks exponential, and it is very exponential until it gets to half the carrying capacity. And then it keeps growing, keeps growing, keeps growing, keeps growing. It's going to grow forever, but then it approaches the ceiling and it's constrained. So this is going to be on the AP Calculus BC exam. This is also interesting because it's an inflection point, which also tells you that it has this highest, the concavity changes. This is the steepest part of the curve. So this is the max growth, right? So that's kind of interesting. And it kind of makes sense, if you think about say there's a rumor around campus. Well, when it's new, it spreads, and more people tell it, and other people tell it. But the thing is that once half the school knows about it, there's less new people to hear it. So it starts to peter out, when almost everyone knows it, there's not that many left people to tell it to. So the growth, So the growth rate starts exponentially. But levels out. And a way that we could sort of describe that is that the limit as t goes to infinity of the growth rate is it goes to zero, right? The slope goes to zero. So the exponential, the differential equation that goes with this does have this ky element. It does have an exponential aspect of it that dominates it when y is not very big. And then it has this other limiting factor, n minus y. Okay, so this is exponential, and then this is the limiting factor. And so at first, the m is actually kind of built in with the k value. But when y gets really close to m, this term gets really tiny and makes the whole thing get really small and go to zero. The closer y gets to m, the closer this term goes to zero, the whole thing goes to zero. Okay, now let's see if we can solve this differential equation. Okay, so we got to separate the variables, dy. In fact, we're going to move everything over to the left-hand side, except for the k. I don't want to move the k. Anything that we can leave on the right side, I want to. But the y and the n minus y, those have to stay together. We'll leave the k over there. And I guess a lot of times we use t. So separate the variables, and then we're going to integrate both sides. Now, the interesting thing here, and this is one reason that we may have not done it last year in Calc AB, is to integrate this, you need partial fractions. Partial fractions, which is really just an algebra technique, but we didn't really make you use it until this year. So partial fractions, you're going to break it up into a over y plus b over m minus y dy. And that's going to equal kdt. So I'm going to do a little work over here. We're going to multiply. So we got 1 over y m minus y equals a over y plus b over m minus y. This is a good review. You guys probably haven't done these in a little while. All right, partial fractions. Multiply through by the least common denominator. You get 1 equals a m minus y plus b y. And you eliminate 1. We plug 0 in for y. And we get a equals 1 over m. Okay, and then we plug m in for y to get rid of that term. And b equals 1 over m also. Interesting. They're both 1 over m. So I'm going to rewrite these over here. I'm going to say, okay, well, this is 1 over m, 1 over y, plus 1 over m, 1 over m minus y, dy. And I'm just leaving the right side the way it is for now until we get more progress on the left side. Okay. I think we're ready to integrate. 1 over m is just a constant. It's going to be 1 over m, natural log of the absolute value of y, plus 1 over m, natural log of the absolute value of m minus y. But be careful here. There's an extra negative here. And the chain rule is going to pop out, and to fix that, I need an extra negative in front. Okay, be careful. Equals kt plus c. Now, I guess we're just going to solve this generally. We don't have an initial condition right now. Now, to clean this up, I'm going to multiply both sides by m and distribute it. Okay. And so then over here, I could also then combine what's left, these two natural logs together using log rules. It's going to be y over m minus y division because that negative. And over here, we're going to write mkt. But m times c is just some constant times some other number. It's just a new constant. So I'm just going to write c. Now, if that really bothers you, write a little c sub 2, but it's just a constant. We've been doing that for a while. Okay. So now we are ready to exponentiate both sides. And I'm going to use rules of exponents to say, okay, well, this is e to the mkt times e to the c sub 2. And this, again, is just some new constant. You can call it c sub 3 if you want. If it really bugs you, but I'm just going to replace it with the c just to simplify things. Then we want to get rid of the absolute value, so we're going to do plus or minus, and I'm going to put the c out front. You can just write c. For those of you that bothers, I'll write a little sub 3 there. Now, there are different... the c is going to incorporate the positive or negative. If it needs to be negative, it'll get figured out in the c, so we can just go with the positive right now. Now we need to solve for y. So what we need to do is multiply both sides by m minus y. So we get y equals, and over here we have m c sub 3 e to the mkt minus y c sub 3 e to the mkt. And so this is just a bunch of algebra. So now we want to get the y's together on the same side. So I'm going to add this over here, and I'm going to go ahead and factor it out. I'm getting closer. And then I'm going to divide both sides by this. And so, I mean, we could say, this right here is the solution, but the way that it's usually presented is a little tweaked on this. So what I'm going to do is I'm going to divide or multiply by the fraction c sub 3 e to the mkt, top and bottom. I'm allowed to do that as long as I do the same thing, top and bottom. So we're just going to change this to the more common presentation of it. So on the top, you just get m. And on the bottom, you get 1 over c sub 3 e to the mkt plus 1. Okay. And then for the final version, so we just have the carrying capacity on top. We usually put the 1 here first. And then 1 over c sub 3, we're going to use a new letter, capital A. And this we're going to write with a negative exponent instead of in the denominator. So this is the logistic growth model that we're going to use. That is, pretty common. So we just did it. We just re-derived it. That was fun. I think we did that back in first semester when we were doing partial fractions, but we didn't do any actual logistic growth. So there it is, from differential equation to solution. Now you're not going to want to do this every time. So you probably want to memorize the solution, memorize some things about it. But you should be able to do this work if you had to. I'm going to give you some problems that are very close to this, and I'm going to expect you to be able to do this kind of work on your upcoming test. So let's take a look at some of the, now that we have the equation, there are some special things to remember. Okay. And so I'll just rewrite our solution right here. Y equals m over 1 plus a e to the negative mkt. And a lot of times we'll set it equal to population, right? It can be y for just some amount, or it could just be population. Now, there's some, in the derivative of this, dy dt or dp dt is kp m minus p. So this is something you should memorize also. You should memorize the solution, the growth model, and the differential equation it comes from. Now, there are some things you could do. I'm going to show them to you just once, but tell you never use them. If you use them on tests, I'll probably just take off points, even if you get the problem right, because it's just not reasonable to memorize tons and tons of stuff. It's more effective to understand what's going on and be able to do it without memorizing extra things. So if you plug in T0, that would give you the initial population. So if I do that here, I get the initial population, and you plug t equals 0 in, and so you're going to get m over 1 plus e to the 0 is 1, so m over 1 plus a. Then you could cross multiply, and then you could solve. And you could get A equals carrying capacity over the initial population minus 1. So, I mean, this is sort of a formula for A, but don't use this. It's really not. It's a couple simple algebra steps to be able to get the value of A. Okay. So, anyways, just in case you saw it somewhere, I'm emphasizing that's how you get it, but don't use it. If you use it, I'll penalize you for it. I'll penalize you heavily if you get it wrong. And even if you get it right, I'll probably penalize you a little bit. Now, there's this thing I pointed out when I sketched it. I said there's this inflection point on the graph. where the growth rate is maximum. And so that seems like something special. Now, what I want to do right now is prove where the inflection point happens. Okay, we're just going to memorize the result. Okay, this is something I think that's worth memorizing because the work involved is a lot. Okay, and so the result is it happens at the population when the population is half the carrying capacity, and I feel like that's an easy thing to remember. It's not really so much a formula, just it's half the carrying capacity. Okay, now let's see if we can prove it. So it would have to be where the second derivative of the population changes sign, right? So we got to get the second derivative. We already have the first derivative, dp dt, and we want to take the derivative of it with respect to time again. The only problem is it's in terms of p, so we're going to have to use implicit differentiation. And so we're going to do a product rule here. It's going to be kp times the derivative of this. Now, m is just a number, so it's going to be negative dp dt, right? Plus m minus p. The derivative of that is going to be k dp dt. Now, dp dt is the expression that we were just taking the derivative of. So I'm going to go ahead. We do this a lot with logistic. I don't want derivatives in my second derivative. So I'm going to replace these, substitute those in. I'm going to move this negative out in front and then put kp m minus p in here. All right. And we can put this k in front. And in here, we're going to put kp m minus p. All right. I'm going to try and clean this up. This is negative k squared p squared m minus p plus k squared p m minus p squared. So I'm just kind of simplifying things here. Okay, so I could factor a k squared p and an m minus p out of both of these terms. What would be left here would be a negative p, and what would be left here would be an m minus p, right? And then we could, I'm trying to get through all this. So k squared p, m minus p, m minus 2p. We're going to set this equal to 0 undefined to try and find inflection points, potential inflection points. So p equals 0, p equals m, and p equals m over 2. That's what we get. I'm going to do a line check, just like I usually do. Put these in order, 0, m over 2, and m. I'm going to test a point. I'm going to test, and it's populations. These are p-values. So I'm going to test 2 carrying capacity. Now, if I plug it in here, I get positive, negative, negative. So it's going to be positive. And it's going to switch signs. Negative, positive, negative. So it's concave down, concave up, concave down, concave up. And sure enough, right here's a carrying, here's your inflection point at half the carrying capacity. Now the growth, the graph looks like this again, real quick. Looks like that, and there's that inflection point. It's concave up, it's concave down. Totally makes sense with what our line check gave us. Now the one thing is, you might say, oh, well, let's get rid of this and this. But there are solutions that lie above this and below this if the initial conditions put them there. So this should be true that it is concave up here and concave down below it if we get solutions in those regions. Because if you look at a slope field for logistic growth, there's a bunch of slopes up here and down here too. I mean, this is the main area of logistic growth that we kind of apply to growth problems, but there are solutions to the differential equation that lie up here and down here too. So I just proved that there is an inflection point, which is going to be that's the critical point for the derivative, which means it's a potential relative max or relative min derivative growth rate, and it ends up being the max growth rate. So that's pretty important if you're looking at the growth of something. Now, I'm going to give you a couple examples that will be helpful for your homework. So find M P naught K time of max growth. Okay, so that's the directions. I'm going to try and fit 4 examples down here. So the first one, I'm going to give you the differential equation. So the information could be given to you in lots of different ways. Now, one of the things that you're going to need to become good at for the AP test is to be able to identify, oh, that's logistic growth, because they might not say. So once you do that, you say, oh, okay, maybe you could write the logistic growth model underneath it just to help you make sure you identify things correctly. So this is your M, that's your K, right? And so that's a couple of the things. M equals 10, K equals 0.06, or often growth rates are described as a percent, 6%. We're not going to worry about the initial population or the time because we haven't been given that information. So on these ones, this is all I want. Let's do another one. Okay. And so this is going to be dPdt equals 0.12p, 12 minus 3p. Now this one's a little more challenging, and maybe it's not clear right away that it is. But people would be tempted to be like, oh, okay, yeah, dPdt, I'll write my, memorize this. I'm going to memorize it. This is one thing you're going to memorize. You go, oh, yeah, this is K and this is M. Nope, that's not K and M, because you need a single P here, and you don't yet. So sometimes you have to manipulate what's given to you. Like this is logistic growth, but it's not, in the perfect form. So we want to divide a 3 out, factor 3 out of everything. So it's going to be factor 3 out. So it's going to make it 0.36p, and then 4 minus p. I'm factoring a 3 out so that this is a single p like this. Now this is your K and this is your M. Okay? Has to be a single p. So you got to watch out. So M equals 4 and K equals 0.36 or 36%. We're not going to do P naught or T on these. All right. Now for the next ones, I'm asking the same thing. We're going to actually, I think, be able to find everything. But this time, instead of giving you the differential equation, I'm going to actually give you the growth, the rate model. And so it might be helpful to write down the formula. It's M over 1 plus A e to the negative MKT. You don't want to memorize that. Okay, so let's see what we can identify here. Here's M, right? This negative 6 right here is the negative MK. Okay, so we have M is 200 right off the bat. That's easy. Okay. We have negative 6 equals negative MK. And so now that we have M, we could solve for K, right? Negative 6 equals negative 200K. So we could divide both sides by negative 200. And k equals positive 3 over 100, or 0.03, or 3%. Okay. The initial population is easy because it's just the population at time 0. So you just plug 0 into this and you get 200 over 1 plus 24. So you get 200 over 25. So we just get 8 for the initial population, right? Instead of trying to memorize the relationship between A and N and the initial population, that's a ton of extra work that you're probably going to screw up, and you just plug time 0, and that's easy. Now, the harder part here is finding the time of max growth rate. We know that it happens when the population is half the carrying capacity, right? So 200 over 2 equals 100. And so we're just going to set it equal to our growth model. And we just got to solve for t. It's a few algebra steps. This is what we're trying to find right here, right? That's what we're trying to find. So I'm going to multiply this over to the other side. And we'll just keep solving. Subtract 100 from both sides. Divide both sides by 2400. Take the natural log of both sides to get rid of the e. And then divide both sides by -6. So it's negative 1/6 natural log of 1/24. That's the time of max growth rate. Not that bad. There's some other versions you could write of it if you want. We could move the negative inside, which is nice. We could even move the 1/6 inside, but that's up to you. So, I mean, those are the valid versions of it. Okay, let's do one more of those. And this time I'll add a little twist just to make it a little tougher. So I'm giving you the logistic model. And the thing is you're like, oh, this is M. Nope. Look, this has to be 1. Okay. It's supposed to be M over 1 plus A e to the negative MKT. You're going to memorize that. You need a 1. So this is kind of similar to the problem right above it with the differential equation that wasn't quite in the form that we needed. So we need a factor of 4 out of the top and bottom. And that would leave you with 50 over 1 plus 8e to the negative 2t. So this is the same thing. It's just tweaked to make it look nicer. So here's your m. M equals 50. And then negative 2 equals negative mkt. So negative 2 equals negative, just negative mk. Negative 50k. So k equals 1 over 25, or 0.04, or 4%. The initial population is easy. P naught equals, you just plug times 0 in and get 50 over 9, or 5 5/9 for the initial population. And then the time of max growth is going to happen when the population is half the carrying capacity. So 50 over 2 equals 25. And you're going to set it equal to, I would go with your new version. It's just the numbers are smaller. You could go with the original if you want. The new one's the same thing. So we're going to get 25 plus 200 e to the negative 2t equals 50. 200 e to the negative 2t equals 25. You can divide both sides by 200. You're going to get 1 over 8. You can take the natural log of both sides, and you get negative 2t equals natural log of 1/8. And so you're going to get t equals negative 1/2 natural log of 1/8 for your max growth rate, time of max growth rate. Of course, you could write some other versions of this. It can be natural log of 2√2 if you really want to simplify it down. So there it is. Today's assignment's worksheet. Try the worksheet, and this is it. This is logistic growth. You guys have to know this for the AP Calculus BC exam. But usually, if you understand logistic growth, the problems are usually kind of easy. They're usually not a ton of work. Now, I'm going to make you guys do a bit of work now as you get used to logistic growth, but I think you'll see that on the actual AP exam. If you know this really good, which is where this work is going to take you, this work is going to help you understand it really well. Then on the AP test, it won't be a problem.